Now in this session, in the previous session I said I'd give you the truth tables for 3 more operations on Boolean variables, and these 3 new ones, what were they called again? Exclusive OR, equality, and implication. So I'll give you the 3 truth tables for those. In all 3 cases involving 2 Boolean variables, A and B, little a and b. Okay? So the exclusive OR, this combined term, A exclusive OR B, it will be 1. Its value, the value of this combined term, with three symbols in it, it will be 1 or true if one of these 2 is true, but only one. Okay? So these 2 cases here. So in this case B was 1, and in this case A was 1. So when one of them, and only one, is true, this combined thing, expression, is 1. And the other 2 cases 0. So when they're both false, this is, A exclusive or B is false. And when they're both 1, this combined expression A exclusive OR B is also 0. And the region is called exclusive OR. So it's similar to the OR, but you had a 1 here with the OR. But now, with the exclusive OR, this goes 0, because what the case that's excluded, rejected, thrown out, is when both of them are 1. So with the exclusive OR, this goes to 0, right? Now, equality, so A double arrow B, that Boolean expression will be true when A and B have the same value. So if A and B are both false, or both 0, then this will be true. Okay, so you get a 1 here. And if both of them are 1, in other words have the same value, like here, this will be true. So you have a 1 here. In the other 2 cases, when A and B are different, like 0, 1 or 1, 0, or false, true, or true, false, you get zeros here. False, false. Okay? So that's the truth table for equality. And the third one, implication, sort of implies, or the sort of the therefore operation. The one thing you're rejecting is if A is true, you can't have B being false. That doesn't make any sense in the context of implication, implying or deducing, the therefore or so or hence. Doesn't make any sense. So you want A therefore B, if you like, or A implies B. You want that to be false if that's true and that's false, because that doesn't make sense if you're deducing B from A. So if B follows logically from A, then if A is true, then B should be true, right? So if that's not the case, then you reject it. So you put a 0 here. In the other 3 cases, you just put 1 by definition. Right, so this is the critical one, that one here. Alright? Now, when you start getting expressions involving Boolean variables, like when you start combining these variables with operations, well, we've done 6 different kinds now, so not, or negation, conjunction, disjunction, exclusive OR, equality, implication. So we've got six different ways we can combine Boolean expressions. Well, the negation only have 1 term, but okay. So it's possible to write equivalent expressions in Boolean variables for all of them. The old 6 we did, using only not and and. That's possible. So they're sort of interrelated. So for example, you can write P or Q in this way. And you'd find, like if you did the truth table of this, say that's on your left-hand side, and you had like equals, question mark, you're not sure, and you had this expression on your right-hand side, you'd find that this one's truth table would be the same as this one. So in other words, this is the same as that. Right? They're equal. They have the same truth values. The same. Now it may not be so obvious. So P or Q is true if not the conjunction of not P, not Q. That's not immediately obvious. But if you do the truth value, if you create the truth values of this and this, truth table of these two, you'll find they're the same. Right? In other words, the list down here for this and this are the same list in the same order. And if the two truth values are the same, the two expressions are the same. And now if P then Q, that's the same as not P or Q. Okay? So again, same comment, to prove that that's the case, calculate the truth tables for both sides, for this and for this. P, how do you say this? Equal? I don't know what the verb is for this. Well, I'll just say if P double arrow Q, then that's the same as this. Right? Again, to show that that's true, that these and these, this and this expression and this expression are equivalent. You can prove that by finding the truth tables for both. So the same comment for all four cases. And this one, P exclusive or Q, that's the same as not of P double arrow Q. Okay, so I'll just say you can show these four cases that that's equivalent to that, that's equivalent to that. In other words, the or expression can be written in terms of and not. The implies expression operation can be written in terms of or. That's and not, in terms of or and not. But we know how to write the or in terms of and or not, so we could rewrite this in terms of ands and nots, so we could rewrite that in terms of ands or not. Okay? And a similar comment for the rest. So in other words, all four of these can all be written in terms of only just these two operations, and not. Okay. Alright, now something called the distributive law. You're probably familiar with this in context of arithmetic. Here's an example in terms of the arithmetic. It should be distributive. Distributive law. So if these are just numbers now, not Boolean variables, but if they're just numbers, then you know that if A times B plus B, that's the same thing as AB plus AC. Right? That's the distributive law for arithmetic, where these ABC are numbers. Now you have something similar for Boolean variables, and instead of times, multiply, and plus, you use and ors. Okay? So by analogy, analogous with this, you have distributive laws, as they're called, for Boolean variables, and so P and Q or R is the same thing as P and Q or P and R. Okay? And again, to prove that, construct the left-hand side and the right-hand side's truth tables. right? And the dual of this, what does that mean? Sort of like the pair, dual, like 2. The dual of that, like its pair, is you just swap the ors and the ands. So here you've got an and, well you make it an or, and here you've got an or, you want to make it an and. And so you do this, that's swapping on both sides, and you get this expression. So P or Q and R is the same as P or Q and P or R. Right? And again, to prove that, same comment, generate the truth tables for both sides. Okay? Now, a few lines here, a remark that this dual, this one here, that works for Boolean variables, but it does not work for arithmetic, which is interesting. So it's, in a sense, because you're talking Boolean variables, remember Boolean variables only take 2 values, true or false, 1 or 0. That restriction allows you to have this dual form. But when you try to do the same for arithmetic, your ABC, they can be any numbers, right? And so I've given you here a counterexample which shows that this dual form here doesn't work when you're talking about numbers. Now, so let's, I'll just try to show that that's true. Okay, so so the correspondence, like here in terms of arithmetic, with ABC and numbers, so you had times plus, right? So times and a plus here. That would correspond to, say, this one. Now, that works, I think. So let's just, now we're talking numbers, so we're trying to show that this dual form, when it's arithmetic, that's not true, that's not valid, it fails. That's what this is trying to show, okay? So let's give A, B and C numbers, let's give them some actual values, and we just, now, to disprove something, you just need to show one counterexample, one case, one example where your generalization does not work, and if that's the case, then your generalization fails. Right? That's what's called a counterexample. Alright, so let's do this one, and what's the correspondence? So the and corresponds to the times, and the or corresponds to the plus. So and would be the times, the or is the plus. Okay, so A times B plus C should equal this. So let's show that that equals that for these numbers. So A, so that's 2, B plus C, so that's 3 plus 5, so that's 8, 16. Okay, so that's 16. And this case, so A times B, so that's 6 plus